we design actually one very basic and simple arithmetic unit, if you remember from the previous class. So this is actually our arithmetic unit. So we design a very simple arithmetic unit which is able to have a sum, subtraction, and increment and decrement. So then we design very simple logic unit which is able to do AND or XOR and NOT. So what we want to do as a next step is somehow combine these two and design for to actually use. Okay, so we want to design or make 4-bit arithmetic logic unit, or we call that ALU. So what it means that you have one unit, usually we have inside the CPU. Whatever we are designing is very simple version of that. So the ALU actually is a unit which is stand for arithmetic logic unit. So that means inside this module you are able to do all arithmetic operation and also the logic operation. So we want to design a very simple ALU or arithmetic logic unit. So this is actually the table that we have. So definitely we should have one table which is explain how it's supposed to work. So I call this A2, A1, A0. So that means this ALU definitely has some address bar, which is 3 input. So whenever you have 3 inputs, definitely you should have 8 different bit pattern. I actually list all that 8 different bit pattern here. And 0, 1, 0, 1, 0, 1, 0. Okay. So I actually okay. So let's just separate these each row. So see, you already designed the arithmetic unit. So back to this table that we designed, okay? So that means you want to do the same thing. I want to just somehow merge these two units, the arithmetic unit and the logic unit inside the one module. I want to just have one module which is able to do both work. So see, you have 4 operations for the arithmetic unit. Here you have 4 operations for the logic unit. So that means the ALU should be actually has 8 different cases, right? 4 for the arithmetic, 4 for the logic unit. So then totally is 8, right? So if I actually select some other color here, okay, whenever that is 30, this is what we want to do. We want actually it's be a AU. So that means we want to have the add. What's the meaning of add? We already actually saw this in the A unit. We want to say x plus y plus c in. This should be the output. So whenever we have 0, 0, 1, it should be increment. So increment means give you x plus 1. So whenever you have the next should be the actually subtraction. So means you should see x minus y as the output. And the next should be decrement, which is x minus 1. We already talked about this. So the next is actually we are done with the actually arithmetic unit. These are the 4 main job of the arithmetic. Now add the logic units. So it should be able to AND. What's the meaning of AND? X and y bit by bit. So what is the next? Should be OR. What it means? It means X or Y. So what is the next? Should be XOR. So XOR means X actually XOR by Y. And the last one is just taken not of the X. That means you get X prime or X actually bar. Okay. So if I actually make a unit here, just I want to understand my module should be actually has how many inputs, how many outputs. Okay, so I just extended these, make something like this. If I consider this as a 4-bit arithmetic logic unit, so how many address bar I should have should be, this is 3, right? So we have on the table A2, A1, A0, right? Based off these inputs, it actually tells what should be the output. So it tells me how many inputs do we need. If you actually tell me how many inputs, I know you understand the both AU and LU. Number of the inputs that we need for ALU. Total number of the inputs, just not, we already have these 3. So then what else we need? How many inputs we need here? So definitely you should say I need to have X, which is the 4 bits. Definitely I need to have Y, which is, yeah, 9, definitely, right? So X and Y. I need one more Y, because whenever this is 3, 0, you need to able to add with input carry, right? So definitely that's a right answer, 9. Okay, so you have C, that's it. So how many outputs we need? So it should be simple. You just take a look to the AU and LU. LU has 4, which is fine. LU has how many? AU has 4 plus these 2. So that means these 4 could be common, but you need these 2, right? Cout and sign, because you do add and subtraction. You definitely you need extra carry and also the sign whenever you have a subtraction. So that means 1, 2, 3, 4. This is for S, but definitely I need Cout or C4 and something for sign. I just use these 2 whenever this is actually in subtraction mode, right? Sign is just whenever subtraction mode is, so which is, you could see where is the subtraction whenever you have 0, 1, 0, this is subtraction, and also whenever this is 0, 1, 1. So that's actually is the subtraction mode. Okay, so I want to design one unit, which is in the general case, these modules should be has 9 plus 1, 2, 3, which is 12 input, and 4 plus 2, 6 output. So that means inside in this unit, based off these 3 inputs, you could do the all arithmetic and logic operation, which is generally called that ALU. So this 4-bit is very basic, but the complex ALU still follow the same design rules. If you understand the basic one, so the complex one is actually follow the same concepts. Okay, so how we could do that? So I actually back here, I say, okay, I understand what I want to design. So the next question is what tools I have. So I say, okay, I already designed 4-bit. I already designed 4-bit AU. I could use that module. So that means the tools that I have is 4-bit AU. I already designed that. So you already know it has 1, 2, 3, 4 input, 1, 2, 3, 4 for actually X and Y. So definitely you need the C in here, because in this case you need actually C. So this is for Y, this is for X, and what's the output? Definitely you have for output 1, 2, 3, 4 for S. You have 1 C out, and you have 1 sign. Okay. So if you have problem these pins, definitely if you back to the what we did in the AU, you see that's exactly the same thing that we already designed. Okay. So this is the first tools that I have. So that means I already designed AU. So I know how I could design that. We already talked about that. We just consider that as a module. Okay. So then today we actually design the ALU, and right now after you design that and understand how you could design the ALU, definitely you could use that as a module. So I have one 4-bit ALU. Okay. So definitely it has just two input, which is the X and this is the Y, nothing else, right, for LU unit. So definitely these X connected to these X. I don't want to make the drawing very busy and nasty. So for that reason, I just put these two separately. This is X, X, this is Y, Y, Y. Definitely these are connected to each other and you have just one X for the whole unit, right? So definitely you have the address, which is so see, this is important. So these are address. I connect this A1. Be careful. A0. See, I connect A1, A0. Okay. Why? Because if you ignore these columns, so see, if you ignore these A2, okay, ignore this column A2. So whatever you have here is exactly in the same table that you have for AU, right? So 0, 0 is add, 0, 1 is subtract, sorry, 0, 1 is increment, 1, 0 is subtract, 1, 1 is x minus 1. So same thing, A1, A0, 0, 0 is and 0, 1 is OR, and 1, 0 is XOR, and 1, 1 is not, okay? So that means I put exactly these A1, A0 to these two address bar that you have. So that means whenever you have A0, A1, and see this, whenever you have A1 and A0, both 0, 0. So definitely these S actually produce what? Produce the X plus Y plus C in, and you have this as S0 here, okay? This is the same thing. If you A1 again 0, 0, you have AND. So you actually have the AND of these X and Y, and that is inside this 0. So you tell me which bits tell us this should be on the output or this should be in the output. So see, I'm talking about this case and this case. Forget about A2, ignore A2, and whenever A0 and A1 is 0, 0, so that means this one, it's produce X plus Y, you have S0 for that, and this one produce X and Y. So the question is, which of these two should be output? So the answer is, you take a look to the A2. So if A2 is 0, definitely this is the case. If A2 is 1, definitely should be and should be your ALU output. So what it means this. It means I just put one mux. So see, I put just one mux multiplexer 2 by 1. I connect these S0 to this and also S0 to this. When this one AU's output should be the real output of the LU, who tells which one goes as an output? The A2 tells. So for that reason, I actually connect A2 here. Whenever this is 0, so definitely the AU should be the output, right? Because based off this table, the output should be the output of the AU, right? And A2 is 0, should be XY. Whenever this is 1, means this case, that means the LU's output is real output. So I call this actually big S0, which is one of these two that you have. Maybe S0 hat, which have a difference. So similar to this, so that means what you need actually another max 2 by 1. You tell me what I should have. I should have S1 from this, S1 from this, and this should be A2. So again, this is S1, this is S1. So similar for the others, right? This is the max 2 by 1. So its input should be, maybe that's better to jump. So this should be this should be connect to this. This is again S2. This is the S2 of the AU. And that one, you should have the mux 2 by 1. So this one input should be S3. And the next one, actually, I did something wrong here, but I could fix that. Okay, so I actually erased everything except for what I supposed to erase. Okay, so let's do back here. So let's do just complete this. This is our issue. So this is S1 definitely. We have these S1 comes here, jump here, goes there. This is S2. And I could have yeah, that's really tough to do that here. So we have to do this. To have these S3 here, just jump from this, jump from this, jump here, jump here, jump here, and connect to here. Okay, so this is S3. So this is S3 of the AU, and definitely the output should be real S3, which is the ALU S3. This is S2. This is S1. If you don't want to mix with the previous S1, you just put the hat. So that's it. So you actually design that. So now the problem is just these two. What we should do with these two, with the C out and C sign. So the answer is whenever these ALU, you work as a logic, so as a LU, so you don't need C out and sign. They should be 0. Whenever you have actually you work as a AU, definitely this should be your real C out and sign of your ALU. How I could do that? So maybe I change the color and I write a circuit. You tell me you agree with this or not. So I actually put 2 AND here. So this is a first AND. This is a second AND. So one of the input of these AND connected to the NOT A2. Okay. And I call this real C out. I call this real sign. And I connect these directly to this as a second with the different color. Definitely jump here, connect these here. And same thing for the sign. Jump here, and connect in, jump here, connect to this. So what is this C out, C on? So see, I put the 2 AND, which is connected to the one input of these 2 AND is A2 NOT, right? So that means check these tables. Whenever you have the LU, which is whenever A2 is 1, it is LU, right? So that means this is 1, the NOT is 0. So that means one input of these AND is 0. Definitely the output will be 0, 0. So that means whenever that is LU, sign and C out is. But whenever that is 0, so which is should be the AU. If this is 0, not is 1. So that means it has no effect on the output, and C out exactly pass as a C out, and sign exactly pass as a sign to the output. Okay. So maybe that's better to write here, because these is maybe you actually here confused. I write whatever I made here is A2 prime, right? A2 prime C out. This is what I made. So the sign equal whatever I made is A2 prime, not and with the sign, okay? That's it. So which is, if you couldn't see here, so this is the function that we made. Okay, so that's it. So what we actually made is one ALU. So arithmetic logic unit, we use 2 units, 4-bit AU, which is we already designed, 4-bit LU, we already designed, and then we are able to somehow mix these two and make one arithmetic logic unit, which is based off this table, able to do the add, subtract, increment, decrement, and or XOR and not. Okay.